Let's talk about existence and uniqueness of solutions to differential equations. So far, the initial value problems we have considered have each had a solution. Do all initial value problems have a solution? No. Consider dy dt equals 2y over t, y of 0 equals 0.5. Let's look at the solutions to this differential equation, dy dt equals 2y over t. There's a way that we can graph the solutions to this differential equation without even solving it, using what are called slope fields. So here are the solutions to this differential equation. Notice that none of the solutions go through the point 0, 0.5. They all go through the point 0, 0. So y of 0 must be 0. If this differential equation is true, it's impossible for y of 0 to equal 0.5. Therefore, the initial value problem has no solution. It's not possible. So when does this happen? When is it that initial value problems don't have solutions? Let's look at this theorem. That'll tell us. The theorem is kind of scary and a little abstract, but you'll get it with enough practice. You'll be fine. Consider the initial value problem dy dt equals f of ty, y of t0 equals y0. If f of ty is continuous on some rectangle where t is between a and b and y is between c and d, so in other words our rectangle is going to look like this. So t is between a and b and y is between c and d. Here's c, here's d. So in essence this is what our rectangle looks like. Okay, if f of ty is continuous on some rectangle where t is between a and b and y is between c and d, with the point t0, y0 in the interior of the rectangle, then the initial value problem has at least one solution, defined in some open interval containing the point t equals t0. If, in addition, the partial derivative partial f partial y is continuous on that rectangle, then the solution is unique, again on some open interval containing the point t equals t0. So based on this, can we guarantee that the initial value problem, dy dt equals 2y over t, y of 1.5 equals 0.5, has a solution? In this case, f of ty is 2y over t, and t0 is 1.5. So can we find a rectangle containing 1.5, 0.5? Here's where that comes from. Can we find a rectangle containing this point, 1.5, 0.5, such that f of ty equals 2y over t is continuous on that rectangle? You bet, because f of ty is 2y over t is discontinuous only at t equals 0. So these are the points where t is 0. F of ty is discontinuous only at t equals 0. So there is a rectangle containing 1.5, 0.5 on which f of ty equals 2y over t is continuous. Yes, we can guarantee that there is a solution because, again, this function is continuous on some rectangle around 1.5, 0.5. Can we guarantee that the solution to this initial value problem is unique? Again, here's f, 2y over t. Well, the partial derivative, based on the theorem that we saw a moment ago, this is based on the partial derivative. As long as the partial derivative is continuous on that rectangle, then the solution is unique. So in this case, the partial derivative, if this is f, then partial f partial y is going to be 2y over t. I'm sorry, it's just 2 over t. Can we find a rectangle containing 1.5, 0.5, here's 1.5, 0.5, such that partial f partial y equals 2 over t is continuous on the rectangle? Yes, because partial f partial y equals 2 over t is discontinuous only at t equals 0. So this function, 2 over t, is discontinuous only when t is 0. So you bet we can find a rectangle. We can find a rectangle around the point 1.5, 0.5, such that the function 2 over t is continuous on the rectangle. Thus, the solution is unique on some open interval containing the point t equals 1.5. So based on this, can we guarantee that the initial value problem we started with, dy dt equals 2y over t, y of 0 equals 0.5, has a solution? So again, in this case, f of ty is going to be the same. It's 2y over t. But in this case, the point t0, y0 we're looking at is 0, 0.5. So we're looking at that. That's the point. Can we find a rectangle containing that point such that this function, 2y over t, is continuous on that rectangle? Well, f of ty, 2y over t, is discontinuous t equals 0. So it's going to be discontinuous at all of these points. So there is no rectangle containing that point, 0, 0.5, on which f of ty equals 2y over t is going to be continuous. So no, we can't guarantee solutions. Maybe it has no solution. So maybe it has a solution, but that solution is not unique. As we've seen before, it really doesn't have a solution.